Capacitors are used in many circuits for different purposes. So we're going to learn some basic capacitor calculations for DC circuits in this video. Capacitors typically look something like this. We have an electrolytic and a ceramic type capacitor. The electrolytic is polarized, meaning one side must be connected to the positive and the other side must be connected to the negative. The ceramic type can generally be connected either way. On the side of the electrolytic capacitor, we find a dashed line, which indicates the negative side. One lead is also longer than the other, which indicates the positive side. However, these are normally trimmed down during installation, so you shouldn't rely on this alone. These two capacitors are represented with symbols like these. Notice the polarized capacitor has a small plus symbol indicating the positive side. When connecting to a DC supply, the voltage of the battery will push electrons into the capacitor, and so the capacitor charges up to the same voltage as the battery. Capacitors are charged nearly instantly when connected directly to a battery, but we nearly always use a resistor. This will delay the charging time, and later on in this video we'll see how to calculate that. Inside the capacitor, lots of electrons have built up on one side. They are prevented from moving across due to the insulating material between the two sides. As electrons are negatively charged, we therefore have a build-up of charge on one side compared to the other. Therefore, we have a voltage difference between the two leads. These electrons are held in place, and the capacitor can hold this charge for very long periods of time. When given a path, they will discharge until the capacitor is empty. Electrons do not pass through the capacitor, they simply build up inside and are then released. The amount of charge stored in a capacitor is calculated using the formula charge equals capacitance in farads multiplied by the voltage. So for this 12 volt 100 microfarad capacitor, we convert the microfarads to farads, then multiply this by 12 volts to see it stores a charge of 0.0012 coulombs. If we needed to store a charge, then we just divide this by the voltage, in this case 12 volts, to see we need 17 microfarads. We can calculate the energy stored in a capacitor using the formula 0.5 multiplied by the capacity in farads multiplied by the voltage squared. So if this 100 microfarad capacitor was charged to 12 volts, we convert the microfarads to farads and then drop these numbers into the formula to see it is storing 0.0072 joules of energy. We know that the capacitor will charge up to the voltage of the battery. So if we connect a capacitor like this, what will the voltage across the capacitor be? It will be 1.5 volts. If we connected a capacitor like this, what will the voltage be? It will also be 1.5 volts. These are just two different ways to connect capacitors in our circuits. We have series and parallel. The configuration will cause the capacitors to perform differently. If we placed a capacitor in parallel with a lamp, when the battery is removed, the capacitor will begin to power the lamp. It slowly dims as the capacitor discharges. If we use two capacitors, we can power the lamp for longer. Let's say capacitor 1 is 10 microfarads and capacitor 2 is 220 microfarads. How do we calculate the total capacitance? Well, that's very simple. The answer is 230 microfarads. The capacitors combine in parallel, so 10 plus 220 equals 230 microfarads. We can keep adding more, such as a 100 microfarad capacitor, and the total is just the sum of all of the capacitors. By placing them in parallel, we are essentially combining these to form a larger capacitor. That's very useful, because if, for example, we needed a large 2000 microfarad capacitor, but we didn't have one, we could just use more smaller capacitors, such as 2 1000 microfarads or 4 500 microfarads, etc. It's also often used for filtering out noise and to provide more current in high-demand circuits. The total charge stored in parallel circuits is just charge equals the total capacitance multiplied by the voltage. So here we have a 9-volt battery and 2 capacitors with a total capacitance of 230 microfarads. As this is parallel, this wire is 9 volts and this wire is 0 volts, so both capacitors are charged to 9 volts. Therefore, 23 microfarads multiplied by 9 volts will give us 0.00207 coulombs. And with the 3 capacitors, we have 330 microfarads. We multiply this by the 9 volts to get 0.00297 coulombs. We can also calculate the charge of each capacitor individually. We just use the same formula for each capacitor. You can see the answers on screen for that now. If we placed a capacitor in series with a lamp, when we press the switch it will illuminate, but then becomes dimmer as the capacitor reaches the voltage level of the battery. Once it achieves this, the lamp will be off. Remember, electrons do not flow through a capacitor because of the insulating material inside. The electrons are simply accumulating inside on one of the plates, and as they accumulate, they are rejecting an equal amount of electrons off of the opposite plate. So a current can only flow when the capacitor charges or discharges. Currently, with the battery removed, there is no way for the capacitor to discharge, so it will hold the voltage at the same level. It doesn't matter if we connect or disconnect the battery, the lamp will not turn on. However, if we provide another path, when the switch is pressed, the capacitor can now discharge, so the electrons can flow through the lamp and illuminate it. This will become dimmer as the capacitor discharges. What if we had 2 capacitors connected in series? Again, capacitor 1 is 10 microfarads and capacitor 2 is 220 microfarads. How do we find the total capacitance? For that, we use this formula. It might look difficult, but it's actually very simple. All we need to do is input our capacitor values of 10 and 220 microfarads. We can type it like this on our calculator or into Excel, which gives a total of 9.56 microfarads. Notice that the total capacitance is now smaller than the lowest value capacitor. If we added a third capacitor of 100 microfarads to the circuit, we get a total capacitance of 8.73 microfarads. So it has decreased even more. That's because by combining these in series, we're essentially increasing the thickness of the insulating material. So the attraction of the negatively charged electrons to the positively charged holes on the opposite side will become weaker. The total charge of the series capacitors is found using the formula charge equals capacitance in farads multiplied by the voltage. So if we use a 9-volt battery, we convert the microfarads to farads and see the total charge equals 0.00008604 coulombs. The total charge for the 3 series capacitor circuit is therefore 0.00007857 coulombs. The charge held by each capacitor individually is very easy to calculate in the series circuits. That's because it's the same as the total charge. Each capacitor holds the same number of electrons when in series. And that's because when we charged the capacitors, the current was exactly the same in all parts of the circuit. The same number of electrons that were pushed into one plate were pushed out of the opposite plate. So each series capacitor can only ever be charged to the same level. The smallest capacitor will therefore be the limiting factor. However, because each capacitor can hold a different capacity, the voltage of each capacitor will be different. We find the voltage of each capacitor using the formula voltage equals charge in coulombs divided by the capacity in farads. So for this circuit, we see that capacitor 1 is 7.8 volts, capacitor 2 is 0.35 volts, and capacitor 3 is 0.78 volts. These combine to the total voltage of the battery, which is 9 volts. Let's say we have a 9-volt battery, a 100 microfarad capacitor, a 10 kiloohm resistor, and a switch which are all in series. The capacitor is fully discharged, and we read 0 volts across the two leads. When we close the switch, the capacitor will charge. The voltage will increase until it is the same level as the battery. The voltage increase is not instant. It will have an exponential curve. At first, the voltage increases rapidly, and then it slows down until it reaches the same voltage level as the battery. We split this curve into 6 segments, but we're only interested in the first 5, because at the 5th marker, we're basically at full voltage, so we can ignore anything past this. Each segment represents something called a time constant. Therefore, as we have 5 segments, we have 5 time constants. So it will take 5 time constants to charge the capacitor from 0 to just under 100%. All we need to do is to calculate how long one time constant is, and then we multiply this by 5. To calculate the time constant, we use this formula. Time constant in seconds equals the resistance in ohms multiplied by the capacity in farads. So we convert our resistor to ohms and our capacitor value to farads, and we see that 10,000 ohms multiplied by 0.0001 farads equals 1. So in this example, the time constant is equal to 1 second. Therefore, 5 of these is 5 seconds, meaning it takes 5 seconds for the capacitor to fully charge to 9 volts. If the resistor was just 1000 ohms, the time constant would be 0.1 seconds, so it would take 0.5 seconds to reach 9 volts. If the capacitor was 1000 microfarads, it would take 50 seconds in total. Coming back to our original circuit, we can therefore calculate the voltage level at each time constant. At point 1, the voltage is always 63.2%. Point 2 is 86.5%. Point 3 is 95%. Point 4 is 98.2%. And point 5 is 99.3%. So the voltage will never actually reach 100%. That's also why we stop at just 5 points. So in this example, after 1 second, the capacitor voltage is 5.68 volts. After 2 seconds, it's 7.78 volts. After 3 seconds, it's 8.55 volts. After 4 seconds, it's 8.83 volts. And after 5 seconds, it's 8.94 volts. If you needed a more precise answer, we could also calculate each point like this. Remember, because this is in series, the current of the circuit decreases while the voltage of the capacitor increases. Once at full voltage, no current will flow in the circuit. If the resistor was a lamp, it would therefore instantly reach full brightness when the switch was closed, but then becomes dimmer as the capacitor reaches full voltage. When we provide a path for the capacitor to discharge, the electrons will leave the capacitor and the voltage of the capacitor reduces. It doesn't discharge instantly, but follows an exponential curve. We split this curve into 6 segments, but again, we're only interested in the first 5. At point 1, the voltage is always 36.8%. Point 2 will be 13.5%. Point 3 will be 5%. Point 4 will be 1.8%. And point 5 will be 0.7%. For example, if we had a 9-volt battery, a lamp with a resistance of 500 ohms, and a 2000 microfarad capacitor, our time constant would be 500 ohms multiplied by 0.002 farads, which is 1 second. So at the very moment the battery is disconnected, the capacitor will be at 9 volts. And as it's powering the circuit, the lamp will also experience 9 volts. After one time constant, in this case 1 second, the voltage will be 36.8%, which is 3.312 volts. At 2 seconds, it's 1.215 volts. At 3 seconds, it's 0.45 volts. At 4 seconds, it's 0.162 volts. And at 5 seconds, it's 0.063 volts. So the lamp will be illuminated for just under 3 seconds. Obviously, this will become dimmer towards the end of the 3 seconds. Okay, check out one of the videos on screen now to continue learning electronics engineering, as this is the end of this video. Don't forget to follow us on Facebook, Twitter, Instagram, LinkedIn, and of course, theengineeringmindset.com.